Hello, dear learners. Welcome back to Lesson BCE YouTube channel. Today, we're diving into electromagnetic induction and Faraday's law at a conceptual level. And hey, don't forget to subscribe and like our channel so you never miss out on our physics lessons. So, have you ever wondered how we actually generate the electricity that powers our world? Well, it all comes down to this one fundamental principle, electromagnetic induction. We're going to explore how a simple interaction between magnets and wires became the spark that lit up the modern age, leading to, well, everything from giant power plants to the very device you're watching this on right now. Wow, that's a pretty powerful statement, right? To really get why one single scientific paper could have such a huge, almost immediate impact, we got to rewind a bit and look at the big question that scientists were wrestling with at the time. All right, so what exactly was this revolutionary question? Well, to really get why it was so important, we first need to understand what scientists already had figured out. So picture this. It's the 1820s, and the scientific community is absolutely buzzing. A scientist named Hans Christian Ørsted had just discovered that an electric current could actually create a magnetic field. As you can see on the left, electricity could produce magnetism. This was a massive deal. But of course, a big discovery like that just leads to an even bigger question. You guessed it, could the reverse be true? Could a magnet be used to create an electric current? This one single question completely captivated the brilliant experimenter Michael Faraday, and it led him to a breakthrough that would, and I mean this literally, light up the entire world. Okay, so this brings us to the main event, Faraday's big breakthrough moment back in 1831. This was the experiment that changed everything. So on this one day, August 29th, 1831, Faraday takes this iron ring and he wraps two separate insulated coils of wire around it. Now he connects one of those coils to a battery, and when he does, he sees this tiny momentary flicker on the meter that's attached to the second coil. And that, right there, that was the big aha moment. See, it wasn't just having the magnetic field there that made the current. No, the electricity was only created in that instant when the magnetic field was either growing, when he connected the battery, or collapsing, when he disconnected it. It was all about the change. So, to double-check this idea, he tried something even simpler. He just took a regular bar magnet and pushed it into a coil of wire, and boom, the needle on his meter jumped. He pulled the magnet back out, and it jumped the other way. But here's the key part. If he just let the magnet sit there, perfectly still, absolutely nothing happened. Okay, so this observation, this idea that it's all about motion or change, well, it needed a new concept, a new way to talk about it and measure it precisely. And that new concept is what we call magnetic flux. You know, the easiest way to think about it is to just picture magnetic field lines and imagine you're counting how many of those lines are passing through a certain area. Kind of like counting raindrops passing through a window frame. So, this magnetic flux really depends on just three things. How strong the magnetic field is, that's B, how big the area of the loop is, that's A, and the angle between them, which we call theta. Here's the kicker. If you change any one of those three things, you change the flux. And that right there is the heart of what Faraday figured out. If you want to create an electric current, all you have to do is change the magnetic flux. And how do you do that? Well, you can make the magnetic field stronger or weaker, you can change the size of the loop, or you can just, tilt it. So this whole relationship is perfectly summed up in what we now call Faraday's law of induction. Basically, the induced voltage is directly tied to the rate of change of that magnetic flux. So the faster the flux changes, the more voltage you get. Simple as that. But wait, there's one more really important piece to this puzzle. Which direction does the current actually flow? And for that, we turn to something called Lenz's law. And honestly, this adds such a beautiful and really intuitive layer to the whole thing. Okay, so here's what Lenz's law says. The new electric current that gets created will flow in a direction that makes its own magnetic field, and that new field will oppose whatever change caused it in the first place. Put simply, nature pushes back. It's really just a beautiful example of the conservation of energy in action. Just take a look at these diagrams. They make it so clear. When you push the north pole of a magnet toward a wire loop, the loop instantly creates its own north pole to push back against you, to repel it. It's like it's saying, nope, don't want you here. So you actually have to do work. You have to push against that force. And that work you do, that's what gets converted into electrical energy. It's not magic, it's physics. And check this out. This is Lenz's law in action, and it is just Awesome. In this demonstration, that pushback from the coil below, that opposing magnetic field, is so incredibly strong that it literally launches a metal ring up into the air. It's powerful enough to completely overcome gravity. How cool is that?
So you might be thinking, okay, that's a neat trick with magnets and wires from the 1800s. But why does it matter so much to us, right here, right now?
Well, because pretty much everything in our modern electrical age is built on this one single principle. We're talking about the massive electric generators that power our cities, the transformers that move that power across the country, and it's even happening inside everyday things like an induction cooker on your stove, wireless chargers, or even the MRI machines in hospitals that save lives. It's honestly incredible to think about, isn't it? Our whole electrified world, the lights, the computers, everything, it can all be traced back to a guy with a simple iron ring and a coil of wire. It really makes you wonder, what simple questions are we asking today that might completely transform the world of tomorrow? That's all for today's lesson. Thank you so much for learning with Lesson BCE. Don't forget to subscribe, like, and share our channel.